Okay. This is a turbocharger. So these are in a lot of cars because it turns out that the limiting factor for how much power an engine can make is usually the amount of air entering the engine and not the fuel. So this thing has two sides. It's got a compressor side, which compresses atmospheric air going into the engine, and it has a turbine side. And this turbine is powered by the exhaust coming out of the engine. These two sides are connected by a shaft. Here's a diagram of the inside of the turbocharger. This is the compressor side and the turbine side. Exhaust from the engine drives the turbine and the compressor are connected by a shaft, so they spin at the same rate. And the compressor draws in air at atmospheric pressure, compresses it, and sends it to the engine.
Now that we've explained our system, I'm going to go into the assumptions and the models we're going to be using for our analysis. Firstly, we're going to be using the continuum approximation. This is an approximation through which we assume that pressure, density, and velocity are continuous over time and space. This is because we can neglect the local variations in molecules and how they're moving. Secondly, we later confirm that the Reynolds number is quite high for this system. This means two things for us. Firstly, we know that we can assume that the viscous boundary effects are small, which is why we can use the mean flow approximation, in which we assume that over a cross-section, fluid properties are the same. This is used later in our analysis. Secondly, we know the flow is turbulent. To negate this turbulence and to render it negligible, we're going to be using the Reynolds average flow, through which we look at the system across time and take the average.
Looking at the compressor side, the air leaving the impeller follows these streamlines through the volute. The curvature of the streamlines indicate that there is a pressure gradient towards the center of the impeller. This pressure gradient is caused by a force from the walls exerted on the fluid. Looking at the streamlines close to the beginning of the volute, you can see that they're closer together and then expand as you go through the volute. This indicates that the speed of the fluid decreases as the air goes through the volute. So we can use the Bellini's equation, since the energy in the fluid doesn't increase after it leaves the impeller and we assume inviscid flow. We can say that the Bellini constant stays the same through the volute, and we can use the Bellini equation to say that since the speed of the fluid decreases as it goes through the fluid, the pressure increases.
All right, so we want to calculate the specific diameter and specific speed of our compressor and turbine. So in order to do that, we need both the shaft speed of the compressor and the pressure difference between the inlet and outlet of the turbine. So in order to so that requires two parameters, m dot and p out over p in for this chart. So m dot we found using this formula right here, which we found online. And so it uses the energy density of the fuel-air mixture ratio, and the horsepower of the engine in order to compute m dot. So plugging these numbers in, which we found online for pump gas, we calculated a mass flow rate of 17.6 pounds per minute. So that gives us m dot right here. So now we need to find p out over p in. So we found this boost versus engine RPM chart, which gives boost pressure, which is the amount of additional gauge pressure that the compressor supplies versus engine RPM. So we assumed an engine RPM of 5,000 RPM, and that allowed us to find the boost pressure. So using that boost pressure, we found P out over P in of the compressor, and we plotted m dot and P out over P in to find the shaft RPM using this solid curve right here, and we found that it was around 115,100 RPM. We also needed to find P in over P out of the turbine, and using that m dot calculation right here, we plotted m dot and found the intersection to find P in over P out of the compressor. This gives us all the information we need to find the specific speed and the specific diameter of the turbine and the compressor.
So in the previous section, we found a value we needed to compute the specific diameter of the compressor. The formulas and calculations are shown here. Similarly for the turbine, we can compute the specific speed, specific diameter using these parameters and the same formulas. The shaft speed omega for both of these is the same because they spin on the same shaft. With these values, we can go over here to this Cordier diagram and plot them. The Cordier diagram shows the specific speed, specific diameter for a wide range of turbo machines and classifies them as axial flow, mixed flow, or radial flow. As you can see in this diagram, both the turbine and compressor are in the mixed flow regime. For the compressor, this makes sense because of its design function. Primarily, the compressor wants to compress air, that way more of it can fit in the engine cylinder, and it also wants to have a high flow rate of air, that way there'll be a consistent supply of air to the engine. These two parameters cause it to have a high specific diameter to pressurize the air and high specific speed to achieve a high flow rate. This puts it squarely in the axial flow, in the mixed flow regime. The turbine is also a mixed flow regime, but its primary purpose is to extract power out of the exhaust air, that way it can keep spinning the compressor. Thus, we would expect it to be closer to the boundary of the radial flow regime, but our calculations confirmed it was actually near the axial flow regime, but this could have been due to the approximations and inherent error in our calculations that we made.